People created reinforcement learning gym envs even for Souls-like games. That's crazy and so cool. So I asked myself, for what game can I do that? Given that Quake 3 is open source and is very well documented, I should be able to create my own gymnasium env for it and use my model of choice, which is stable baselines 3, to train it for a capture the flag. A quick disclaimer, I left the shooting out, so the goal is only to move to the position. Starting the project, there are many questions to ask. Firstly, how do I set up UDP sockets for communication between my gym env and the running game? And secondly, is the state space continuous or discrete? And what actions and observation space data shall I use? Plus, also, where do I get the flag positions from the map? Point, setting up UDP. Building Quake from source is significantly easier than other open source games, but there's an important caveat. Quake runs in virtual machines. That means it uses QVM files, and they didn't let me use UDP, at least from the server side. I tested it via the client side and that worked, but the important information that I need is stored on the server side. Setting this param to 0 loads the DLL instead of the VM, and UDP works. I do not know C and Quake code really well, so Claude helped me a lot here. It told me where to register the new file and basically wrote the whole UDP setup on the Quake side. When running, I came across the snapshot problem. I cloned repo again, re-added Claude's code, and I still don't know why then it worked. There's a lot of information on the attack-free engine in Quake 3 architecture, and one topic is this snapshot thing. So there is this client in the server, and the server updates the client about the information, and they also communicate over UDP. And there was probably a connection mismatch. With that out of the way, the next question to ask is it a continuous or discrete action state space? The taxi gym env is discrete. We have a 2D grid which computes a total of 5 different states. We have 5 rows, 5 columns, and 4 possible destination locations. So also the actions are like north, south, west, pick up, drop. So Q-learning can just compute via a formula how well an action is. Then we have deep Q-learning, which uses a neural network, as the name says, to compute the Q values and is therefore better suited for large state spaces where you can't just make a table for every state. But I chose to use a PPO, which is proximal policy optimization, and in my case it is stable baselines 3, which also uses a neural network but creates a policy that samples actions and updates the policy. So there's a lot of math behind it. The answer is Quake is continuous. First thing you might notice is that it is 3D, but that doesn't really make a difference. There can be top-down games that have a continuous space and then 3D games that have a discrete space. What actually forces the continuous action space is that movement is driven by real-valued forces velocities, and the fact that you can say move 0.9 in x instead of just move is the real cause. Because of that, the PPO has to choose from a continuous range of actions per state and not a small fixed menu. After that, I was finally ready to create my environment. The gymnasium docs do a really good job to walk you through the important questions you need to ask about your environment and the functions you need to implement. When I first thought about the observation space, I gave the player first only the flag position and the player position and the distance between them. I didn't even think about the hit wall, which is kind of stupid because this should be punished, obviously. But furthermore, I didn't think about yaw and pitch. This is when you look up and down or right and left. dx, dy, and dz are the already computed distances between the flag positions and the player positions. The PPO outputs 3 continuous numbers every step: forward, right, and jump, each between -1 and 1. Forward and right get sent straight through, but for jump I had to add a threshold. Over 0.5 it counts as a jump, and below it doesn't. The flag positions, however, aren't in the code, they are in the map. Fortunately, it's easy to create Quake 3 maps with GTK Radiant. As I mentioned in my Jedi Knight Academy video, it uses the same engine, so you can create maps with this tool as well for Jedi Knight Academy. The maps are saved as BSP files, and fortunately a Python tool exists that can extract class names out of these files. For some reason my map was loaded without a flag, so I couldn't use my own one. So I had to extract the first map from the first pk3 file. I used a pk3 extractor, but the files were empty. But Claude managed to write me a script that extracted them. So that gave me the exact coordinates of the red and blue flag I could then use in my env. And then it was time to put my environment to the test. I set the flag capture limit to 0 so the match wouldn't cut training short partway through. Watching an RL agent train is like watching a fly trying to find its way out of a room through a wide open window. The exit's right there, but it can take a long time until the agent uses it. Early on I had the SVFPS value set to a low number. It's saying how many times per second the server runs physics calculations and updates game logic. I increased it to 200, that made steps the agent could take in a second significantly larger, since it got information from the game much faster. What happens during training? At each step, the agent takes one action and in return collects an observation and a reward. This is called a step. It repeats this for 2000 steps, that's one episode. Once an episode ends, the policy, the network from the graph earlier, gets updated based on everything that happened during that episode. The agent is then reset back to its starting position. The reason isn't optional, it's necessary for the underlying math calculations to work correctly. Which raises the question, how long does this actually take? The number that matters is total time steps. I set it to 319k, which puts the full run at 319 divided by 44, which is roughly 2 hours. I had a thought coming up during training that reducing distance to the flag could reduce training time. But proximity alone doesn't get you a bulletproof policy. Here's the problem I encountered. The agent reached a ledge too high to jump up to. To get around it, it had to turn, meaning change its yaw and take a staircase to the left or right. The problem was that turning away from the flag temporarily increased the distance to it, which a distance-based reward would actually punish. I had problems changing the yaw for UDP, so I talked it through with Claude to look for better alternatives. My idea was to draw something like a red line. The agent could walk along something similar the AAS files next to the BSP files do for the bots to navigate. So it wouldn't need to reason about turning at all. So instead I walked the route myself, tracked the coordinates along a straight path and added them to my environment. The agent was now rewarded for staying on that path of coordinates on its way to the flag. This entire path tracker was written by AI. In my environment, I saved the PPO after training completed, so I could then just load the trained model in the game. I did this for only short distances, but at least it's a start. Thank you for watching the video and see you in the next one.